Hi there, and good evening, everybody. Welcome to tonight's Modular Meetup event, High Performance AI in the Real World. My name is Chris Hoge. I run developer relations for Modular here, and we have a really exciting evening planned for you. We have 3 speakers tonight. Kicking off the event, we are going to have Chris Lattner, CEO of Modular, present to you the Mojo roadmap and vision. If you've been kind of following along in our community, you may have noticed that we just posted to our docs both a Mojo roadmap document, which is outlining our plans and our goals for Mojo over the next few years, but also the vision for what we want it to become. So Chris has prepared an incredible talk for you, where he's going to talk about Mojo and talk about the future of high performance computing. Following up with that, we have Feifan Fan from Inworld, who is going to talk about production-ready voice AI and how they're optimizing text-to-speech for almost any application that requires realistic interactive, and low latency text-to-speech, for games or for other interactions. Have an awesome demo plan for you there. And then finally, we're going to wrap up the evening. I will give a bit of a technical deep dive in how to optimize matrix multiplication using Mojo on GPUs. We have food over in the side room over here, so you should please help yourself. For all of you who are watching virtually on the live stream, welcome. We are so excited that you're here. And to kick it off, I'd like to welcome Chris Lattner up to the podium.
Awesome. Thanks, Chris. Welcome, everyone. Welcome to the folks who couldn't make it in person, and also hi to the ones that could not. All right, so I'm going to start and kick things off and give an update on what we've been up to, but channel it into what are we here to do, why, and what does it look like in the path ahead. So I hope this is interesting and informative. We'll dive in. So for context, I think that, and thank you for joining us. So context, I think many of you know roughly the problem, right? AI, GPUs, TPUs, NPUs, all the PUs, they're all amazing. We all know what they are theoretically capable of doing. But the reality is that fragmentation and the complexity of working with all this stuff is just a huge pain, right? And so the potential energy of the system and the reality of where we are is quite far separated. There's all of this hardware, and the AI systems we have are all amazingly awesome, and there's lots of people innovating and building into the space, but with it comes all these different systems. And so what we're seeing is some of the biggest organizations in the world with elite teams of hundreds of people. They can achieve amazing results. We can see research breakthroughs, we can see product innovation, but it shouldn't just be them. Like, it should be everybody. We want a lot more innovation. We want even more progress. We want things in small form factors as well as the big ones. And so this is what we're here to solve. So we've seen many approaches on this. We've seen lots of different systems across the years. I've worked on some of them also, and they didn't work out. And so you might be wondering, are we just doomed as an industry? Should we give up and go home and stop trying? Of course, that's not what we're about. That's why you're here, right? Of course, we're not going to give up. We're going to actually do something about this. So today we'll talk about Mojo. We'll talk about what it's about, kind of why we're doing this, what problems we have to solve, how we're thinking about it, and then we're also going to talk about the steps from here to, ultimate world domination or whatever the future holds. So first of all, don't think of Mojo as a language. So Mojo is a programming language, yes. I mean, that is literally true. But the way I think about it is it's a foundation. It's a foundation that we can build on top of. It's a foundation for a lot of amazing things, some of which Modular will help build, but it's the foundation for a lot of things that have yet to come. I was talking to somebody about building amazing new UI frameworks and amazing new other capabilities, because we're standing on the precipice of a new form of compute. And when you have a new form of compute, it changes the dynamics, and many of the assumptions, many of the systems that were built, many of the existing software frameworks, while valuable and important, and we don't want all software to we don't want to rewrite all software for the sake of rewriting software, but it gives us an option, an opportunity to rethink the principles, the assumptions, and what we're here to do. And so Mojo, again, it will take steps, and we'll talk about the steps over time, But it really does represent to me an opportunity to think about this, because I know developers, I know platforms, I know the capabilities. And when you have such a big hardware shift, I think that it's just such an amazing time for us to build into this. So as Chris said earlier, we shipped a new document. And so if you haven't taken a look at it, you can see it on docs.modular.com, Mojo Vision. And so what it does is it lays out, how did we approach this? Why did we decide to do this? And so this talk is kind of going into unpacking that a little bit. I'll do a terrible job of summarizing it, but different multimedia form factors, you can make fun of me later. If you can read way more details on the doc that's public. And so let's start with the modular mission. So why is modular here? It comes down to this phrase, democratizing AI compute. And this phrase is very important to me. And I've been writing in my spare time an epic blog post series. I'm sorry, I'm behind. I need to get back up on that. But let's dig into what these two terms mean. So the word democratize, it's a social statement. This is a statement about humans. This is about enabling more people to participate. This is about unlocking creativity. This is about coming back to the human potential, the ideas. Like I talked to students in high school. There's so much latent potential out there. So many people that want to do incredible things, have amazing ideas, but then you run into this problem of complexity and this problem of all these systems and just the legacy architectures we've been building up. And of course, AI, well, I say AI because that's what the entire world wants to talk about, but it's really about compute. It's about accelerators. It's about all the different kinds of systems. It's about what these things enable. It's about the different form factors. It's about the different applications. It's about accelerators, yes, for matrix multiplication, but also someday for video transcoding and networking and all of the different things that the world needs to program. And my bet, I think many of us have seen, is that it's not that compute's going to get homogeneous and unified and there's going to be one CPU that wins the world. We're at the end of Moore's law. Things have changed. Physics has shifted. Building chips is really important for the world, even on a geopolitical level. And so what I bet, and what I think we'll see, is we'll see more compute. We'll see more silicon. We'll see more diversity. But we don't want to rewrite all of our software every time a new chip comes out. And so this is what Modular is about. So we built Mojo from scratch. It's a whole new programming language. It is separated out from the rest of the existing systems. And that's really crazy. It takes years to build something like Mojo. It takes years to build an entirely new ecosystem and language from scratch. And so I get asked all the time, why did you do this? And honestly, this is not a thing that we wanted to do. This is a thing that was necessary to fulfill the mission. We looked at different things. And so if you go out there and you look at this, well, if you're programming a GPU, you're almost certainly doing it in C++. CUDA, RockM, Sickle, like almost everything in compute is written and built with C++. And I love C++. I've written lots of it. I also really hate C++. It's okay, but it's also 40, 50 years old. It's a terrible user experience. It's archaic. It's holding the world back. Also, I mean, I'm not going to go into it. The compiler situation is a mess. Partially my fault, but but this is the de facto default option, right? But the world's shifting. Python, it's a thing. The entire world of AI is not in C++. A lot of people are pushing into Python DSLs, and so the other option would be to say, okay, well, let's just take something with Python-y, hack it up really quickly, get a prototype. But the problem with this is you don't get something that's actually good. And I was talking to some other folks here earlier today. When you're kind of deciding to take on an epic world-scale systems problem, there's a sense of responsibility that at least I feel to make sure that given that opportunity to do something about this, we actually do it well. I guess it can take years of time to do this. It's a really hard problem. Success and winning can be world-changing for so many people, so many different systems, enable entirely new chips to be successful. But if you're going to do that, let's do it right. And so what we did is we decided to do the hard path to get to a better result and really invest and do this the hard way because we felt that was really important. So how did we approach it? Given that we're crazy enough to do this, now you have to decide what you're doing. So I think many of you know Mojo is a member of the Python family. Well, that's, I think, easy to explain today. AI is Python, but Python's also the most popular programming language that exists by many metrics. Lots of people know Python, so let's meet people where they are. And Python has many challenges, but the syntax is fine. So, but Python's not good enough in other ways. Like you can't program like hardcore performance GPU internals with this. And so let's build something that can scale. Let's target these crazy accelerators that are so important to us. Let's build large scale libraries. And finally, AI, yes, GPUs get all the credit, but CPUs are really important. Like systems programming, making stuff that's safe and secure and high performance. This isn't just about AI and GPUs. This is something the entire world is starting to realize is important now that power and everything else becomes even more important. And so we want low-level performance and control. And so these are things that we're bringing together, and there is no system that does this. And so what are we betting on? Okay, so now you're going to do it. You know you're going to do and try to achieve these things. We need to make some bets. And so one of the bets that's very controversial among my compiler friends is we said, you know, compilers are actually really awesome, but we want to shift a lot of the logic, a lot of the algorithms, a lot of the complexity of AI out of the compiler. Let's put it into Mojo code, because I love compiler engineers. I have dabbled in this field. But there's so many more people that can write normal code and can look at syntax and can reason about it and invent new algorithms and understand hardware than there are people that know compilers. And so to do this, we made a major bet. Let's push that complexity from the compiler into code, and then let's make it as generic as a compiler can do by bringing the power of generalization into Mojo code. And so if you've played with Mojo, you see it has a very powerful metaprogramming system. You can do things that typically you'd have to write compilers to be able to transform and do loops. Vectorization is a library feature. Well, this is a very big difference about Mojo and other systems. And while there's definitely analogies, this is something that's very important that we're betting on. And they are. So compilers are important, right? It turns out that many of the systems I've worked on, you know, Swift and Clang and many other things like that, but also Rust and Julia and many of these other systems were built on much older compiler architectures. And so given that there's this new technology, these new devices, let's lean into building and investing in the best in class architecture of the time. And then it's not just about kernels. And when you start digging into these systems, when I look at AI frameworks and PyTorch and TensorFlow and Dynamo and XLA and like all this technology that's been built up, there's many of these cool systems that have been built with a lot of really great capabilities, but they're built against the kernel design. They're built against the source code. Again, they hard code things into the compiler. Many of these algorithms actually have nothing to do with tensors, but AI has been fueling and funding innovation in AI compilers and in the space. And so if we can take this, if we can integrate this, if we can generalize this, if we can make it so you can get automatic kernel fusion, you can get memory planning, you can do this against arbitrary data types, well, suddenly, I believe, you fast forward, there are many different kinds of parallelizable data structures, and we can bring and generalize this technology into a new place. But you can only do that if you have the extensibility of source code. And so that's a feature that's kind of dark hidden that we're using, but it's one of the major underlying bets of Mojo that will play out across the years. So now you're also building a new language, and I've done this before. And one of the things I've noticed is that it all starts great and fine when you're early on, but then you keep adding stuff and adding stuff and adding stuff and adding stuff, and suddenly many of the systems programming languages that exist today end up spiraling this gigantic pit of complexity. I'm looking at you, C++. And so I don't know if we will be able to avoid this. I hope so. This is actually really difficult for lots of good reasons. There's a whole tragedy of the commons thing that goes on with programming languages, where every individual feature can be justified. It solves one person's problem or one cohort's problem, but then everybody suffers from the aggregate complexity of the systems. And so what we're trying to do, and so again, ask us in a few years if this has worked out, but what we're trying to do is control complexity. And that's something that we as a team talk about quite a lot, of how do we keep things simple, orthogonal, composable? How do we make it so we can implement things in the library instead of the compiler? How do we rein in and control this? And there are things that we're doing, and we can read about it in the doc, but this, I think, is actually one of the things that Python did really well, maybe not perfectly, but did really well that caused it to be as accessible and as scalable as it's been. So that's just a brief tour of the vision of what we're trying to do. If you have a vision, you have a North Star, you know what you want to achieve and go after and make that happen, you then have to game plan. How are we going to break this down? This is a many-year journey. Now, Mojo's now 3.5 years and 2.5 years into its development, and we have many more years to go. And so what we did as a dual to the vision doc is we published a roadmap. And so the roadmap kind of breaks the evolution of language down into a few different phases. Step number 0, because we're nerds. Bring the dang thing up. And so turns out there's a lot of really basic low-level work you have to do to get anything to work, and particularly something as bold as what Mojo is trying to do. When you're trying to push a lot of complexity out of the compiler into the library, there's a lot of these fundamentals that have to be right for you to be able to build things. And so in our case, it was, get the CPU GPU divide, get the runtime integration, figure out how structs and composition work, even figure out how generics work, traits, these basic language constructs need to be in place so you can then build libraries, and so you can then build generic algorithms. When we did this, of course, we're running fast, we're trying to build lots of things. You use the language you have, not the language you want. And so we built a lot of stuff and it became a fragmented nightmare. And so as kind of the consolidation phase of this phase 0, we then got traits into language. We got these capabilities in there. And so we clawed back a lot of libraries and reconsolidated. At one point, I think we had 4 or 5 different pointers. So now we have one, or well, an unsafe one and a safe one. So today we're focused on phase 1, or what we call phase 1. And let's build Mojo as a very high performance GPU, CPU programming system. And so when you break this down, again, we're squarely into this. There's 4 phases. One is make this metaprogramming great. So high performance generic algorithms, the metaprogramming features, but also polish the core language. We want collections and algorithms and for loops and closures and all this kind of stuff to be great. And so this is, it's a lot of very low level work, but each of these features then unlocks new capabilities. We'll talk about one of those later. Again, Python is really important. The ecosystem out there is vast. And one of the things that's very important to us is we're investing in making it so you can take an existing Python package and just extend it in Mojo. Right? A lot of us have worked on large scale Python systems and it's all fun and games until suddenly you care about performance and you find yourself writing C++ or Rust or C or something like that because you care about performance. And now you're in this dual world of curly braces and tabs. Like it breaks your brain to do this and you have all these bindings. Turns out Mojo has a really great way of doing this. And so making Mojo be the best way to extend Python is a really great way to, again, meet people where they are in Python and lift them without having to switch over to a completely different system. And so we have the basics and beginnings of this, and we're continuing to invest quite a lot in this. Finally, we think that phase 1 will probably be a 1.0. And with the 1.0 comes some expectations of stability. And so we're in planning phases for this right now. I don't have an exact date, but giving stability to the ecosystem is a really, really big deal and something that we're very excited about. And so as we're thinking about this, as we're leaning into this, this is what gives us the platform capabilities, and you can read about the specific features in the doc, that allow us to get to that kind of 1.0 moment. Now, when you do that, you take the next step. That's when we can open source the thing. And that's something that I think we're all very excited about. And yes, it will probably be a logistical nightmare for the team and they'll have to deal with tons of bug reports and other stuff and whatever, but this will be a very big deal for us, for the team. And I'm happy to say we're on track. And so we've committed to doing this by the end of 2026. I think we can do it quite a bit earlier than that. So maybe earlier in 2026. And the team's working really hard on this. I know that many people in the community are working on improving standard library and kernels and learning and battle hardening, all this kind of stuff. And so I'm very excited about this phase. So you get past phase 1, what's next? Well, this gives you the ability to build high performance code. So you got the foundations. You can write GPU kernels, you can write high performance, you can extend Python packages and do all this kind of stuff. But there's a lot of actually really cool things that go beyond this. And that's when you get into the more application level. So I would like to stop writing C++ someday. That is a life goal of mine. And so to do that, you need to build up a little bit higher in the application level. You need to add some more features. There's many systems out there, including Swift and Rust and these kinds of languages. And so when you get into phase 2, this is where you start to say, let's add like really efficient async. Mojo has some of the basics of this now, but we can build this out better. Let's build out dynamic traits, pattern matching, which theoretically could come into phase 1, but we'll see. These other features can make Mojo feel like a really great language in the space where suddenly all of systems programming that people are doing becomes available. We also have a really amazing start and a memory safety model. And so Mojo has a air quotes borrow checker. It's not a borrow checker, but it has a replacement for a garbage collector free, deterministic, and predictable memory management system that's also safe. We need to finish this out, bake this out, maybe add public and private so we have some access control and other kind of basic things. And you get into something that's now suddenly memory safe and a very nice way to build large scale systems. But there's also a lot of other things we can do. And there's a lot of latent potential in Mojo. And so we've been very deliberate about being focused, and there's a lot of really cool things. For example, having a macro system so you can actually just add a parallel for loop and have it feel like a for loop. That's actually a big deal. Somebody was bugging me about FPGAs, right? And if you want to target really weird accelerators that are inherently parallel at all levels, you don't really want imperative control flow. You want to be able to extend the language, and you want to be able to create new expressive capability that actually maps onto your system. And I don't want to do that by hacking the compiler for every new chip that comes out. I want that to be in the library. And so we can invest in features like this. Another is, we talk about this MLIR thing and the compiler architecture and these other aspects that we have built into the stack. Again, I'm trying to keep the team focused. Can't do this today, but making it so you can say, hey, if you have string add and a string add, why don't you do string concat? Why don't we have it so that people writing libraries can write people optimizations and can write other kinds of transformations that apply to their data types, rather than everything being hard-coded into the compiler, and make this an open and extensible way of expressing algorithms that then everybody can participate in. And so we have some of the bones for this, we have some of the ideas, but as we get into this, now suddenly you can unlock that next level of performance, that next level of capability that, again, library developers can build into their libraries, but then users of those APIs don't have to know about, they just get good performance. So this phase 2 is something that we're not scoping right now. Let's get phase 1 done as soon as possible, ideally early next year. But I think this is going to be another huge epoch, expand the set of capabilities and the use cases, and we can grow into this. When you look beyond that, you suddenly get into, okay, well, actually Python is pretty great, right? I mean, it does own the world, and a lot of the things people are doing are very dynamic. And while you're not going to run super dynamic, crazy stuff on a GPU, maybe, it actually allows you to build really beautiful APIs and expressive systems. And so what we will do is we'll then layer on top of these other steps and say, okay, let's start building into this, the really amazing class features and other things that Python users expect. Let's get that fully dynamic object model in place that include all the things that you'd expect for this. And then let's add this code migration assistance. Now, I've been given grief about this, like, it has to be exactly perfectly compatible with Python. Turns out C++ is a superset of C, and it's not perfectly compatible with C either. And so I don't know that we have to be perfectly compatible with Python, but we definitely want it to feel like Python. We want to make it feel like a good member of the Python family. As we invest into this, I think that this is going to be a very exciting time, because we'll have a very dynamic, very expressive language where, yes, you can go all the way down to the metal, you can program GPUs, you don't have to switch systems. And to me, this is another big part of the unification. It takes time to build these systems, but when they're built the right way, they compose, and then you can solve for many different cohorts, enable many different applications and use cases, and then have it actually add up to the right thing. So to pull it all together, we're past this phase 0, we're charging ahead, we're well into the phase 1. New features are landing every day, it's very exciting. Phase 1, I'm very confident is 2026. I think maybe earlier in 2026. And then we start building into this, and we can build this in each step along the way. We can unlock new capability. And if you want to know what each language feature is and all that kind of stuff, you can check out the doc. So that's a high level, super high level view of the roadmap. But let me tell you about some of the cool stuff that's happening now. And so these include some very small things. Like, so coming tomorrow, I think, like, Mojo gets the ability to have default trait implementations. And so what this means is that you can write mixins. And so if you have, in this case, like an equatable trait, you can say, hey, for equatable, you can just implement EQ, and I can give you a not equal. And so all this does is it's a very simple feature. It means that you can write less code. And so this is what I mean by investing in getting the basics right, making it super simple. And yes, you can just write equals. And then now, not because Mojo knows anything about equality or not inequality, you just get not equals for free, right? Very simple stuff, very easy, and it just kind of builds into this and makes the language better. And deletes a lot of code. Also tomorrow, we're starting and embarking on a new engineering blog post series where we're saying, okay, well, there's these amazing accelerators like Blackwell. Blackwell is a really cool, very advanced device. It's not the kind of thing where you can just throw some for loops at it and have it go fast. Let's break this down. Let's crack this thing open. Let's actually teach people how to program these things. And a lot of the APIs and the higher level kernel programming things that Chris Hoge will be talking about later are making a lot of progress. And as that's happening, it's making it easier and easier to program these advanced accelerators. Another cool thing, if you use VS Code, you maybe have used the LSP extension. We've had 2 different LSPs, one for the nightly, one for the stable. It's been kind of complicated. Sometimes it crashes. And so we have a whole new LSP that's about to launch. It's really awesome. It's way faster. It has a lot of improvements in it. And I think this is going to be a big upgrade to the lived experience for Mojo programmers everywhere. Another thing, so we have Conda in the Mojo ecosystem. We're also bringing this all to pip. And so this is a really big deal. And the way we factored the packages is that we're factoring it so you can install just the Mojo compiler. You can install the Mojo developer toolchain. You can install Mojo and Max together. You have a lot of optionality in terms of how you build these packages. And this is a big deal because if you're building a Python package, for example, and you want to extend it with Mojo, we don't want to depend on the entire development ecosystem. You want to say, hey, just build this package, bring in just the Mojo compiler by itself, and now we can make this very low dependency, very simple and easy to install experience. And so I'm really excited about this. Another little thing that's coming, it's actually already in the build, but we just haven't told anybody about it, but there's this vendor, this fruit company up the street that makes some really cool devices. And so we're just now getting support for Apple GPUs. This is pretty cool. So this is, I don't want to oversell this. This is the beginning. This is not the end. We're just getting the support in the system. It's limping, and you can do basic math. But I'm really, really, really excited about this because this is now, it's open source, and you'll see it. This is something that we can now build into together. And there's a lot of work to be done here, but turns out the Apple GPUs are extremely powerful. They're extremely pervasive, and I'm really excited about being able to program GPUs on my desktop now, instead of having to SSH into a Linux box on the other side of things. And so I think this is very exciting. This is also, again, the opening this up to new hardware. It's a capability that's very, very, very exciting. If you want to super nerd out, support for Apple GPUs was added by an intern at Modular this summer. Amir is amazing. He gave a nice tech talk, and check out the community, the Modular community YouTube stream, and you can see him talking about what it takes to add a new device and what that looks like. And so we'll be shipping this. I think it's in the nightlies now, but it'll probably be explained soon. So anyway, so I'm gonna wrap up my talk. You know what we're here to do. We're here to crack open this world. We want to actually get a lot more people involved. We're open sourcing the stack progressively. Today, you can contribute to the standard library. There's a lot of cool stuff going on there, particularly with a new language feature comes in, and suddenly a lot of things can be upgraded and changed. We have the GPU kernel library, and so if you want to work on amazing kernels for Apple GPUs, please help. We have new models and pipelines and hundreds of models available. We have Max Framework, and I'm sure that everybody will keep reminding us that this thing's not open source, but we will actually get there actually quite soon. So if you do actually get a swag, you can look like this fine gentleman and get a t-shirt. And so please do join the community, and I would love to work with you on GitHub. So with that, I will also give a shout out. Modular is growing. We have a whole ton of job postings online. Please check out our career page. And if you think you'd be a fit for the team, then please do apply. And with that, I'll hand it back to Chris.
Oh, thank you so much. Yeah, Chris, do we have time for questions, or do we want to? Yeah, does we have maybe a few minutes for questions? If there's anything you'd like to ask, and I'll grab a microphone and bring it around if you have a question.
Sure. I guess you've convinced me. What, in the back, Chris?
Yep.
Sorry, I'm just too excited. You said in the nightly build, so there's the Apple support for the GPU. Can I get that?
You two are allowed to download the nightly builds. And so I believe it's hidden behind an environment variable or something right now. But I nominate Brad, who's here, to answer this question. Brad, what is the plan? Thank you, sir.
Yes. So yes, yeah, it's very basic. I will say I'd be very cautious. We're very excited. It is very basic right now. We are rolling out features as we speak. We are leaning into the nightlies, putting it what everything that's out there. I can post the environment flag in the forum. Like we have a little bit of a thread on it. People are asking about it already. So I can post. It's gated behind an environment flag. I think it will wait until the next nightly. So the next one you'll get default trait implementations and the basics of this. It should allow you to run our vector addition, like function example. So you can add two vectors together, which is very exciting. It's like great capabilities. It's got to start somewhere. So you'll see the basics there, but we've got to build out a few more parts before we're going to gradually get all of our GPU examples one by one working. And then what we'll do is we'll engage the community and have a longer post about here are all the things we'd love your help to, intrinsics to build out, kernels to optimize, things that can be worked on in parallel, because we're trying to get as much as possible to be able to be built in the libraries. So
you said tomorrow?
yes, tomorrow.
Okay, so there you go. It's going to make you wait 8 hours or something. See how he is. Any other questions?
Hi, I know MLX on Apple GPUs has some Mojo within it. Is Max, when it's running on Apple GPU, expected to be more performant than MLX in the inference area?
Yeah, that's a great question. I have no idea. I haven't used MLX in quite some time. It depends on how much we as a community invest in it. And so there are architectural features we have that MLX doesn't. So we have, for example, kernel fusion. My understanding is that MLX builds on top of metal performance shaders and some of these other hard-coded kernel libraries. And so I think we need, again, as Brad said, this is all very early. Let's build into this a step at a time. But as far as I know, we can do everything they can do, but better. And so, and open source, which is also a big difference. And so, but I've forgotten everything I know about Apple GPU programming. And so I think we need to we all need to figure this out, and let's start with vector add, but then let's build a really fast matmul, and then everything else lights up. So one of the other things I'd say about MLX, it's a great system, of course. As far as I know, they have really basic CUDA support, not anything real, and AMD probably not. And so that, it's a great system, but it's not designed to be portable and scalable. So. Yep.
Thanks, Chris. As Mojo becomes more complete Python replacement, what do you envision in the future? Are they going to coexist side by side? What's going to happen?
Well, so I don't think Python has anything to worry about. I don't think Python's going anywhere. How should I say this? I'm an ambitious person. I want to build things that people use, right? I want millions of people to use Mojo, and I would love to see it be the default that takes over some chunk of compute, obviously, right? But that doesn't mean that Python has to lose, right? And so this is where it's not a zero-sum game. I think that what I would love to see is more people get into new forms of compute. I'd love to see people use Mojo. I don't think Python has anything to worry about. And so, yeah, he's asking if we still use Python. So yes, we do use Python. The Max framework, the APIs for ML modeling are Python, for example, because Python has way better support for classes than Mojo does today. So now as Mojo grows up, maybe that will be reevaluated. I'd love for that to happen, but the whole stack is evolving and changing, and we're using the right tool for the job. So, yep. Yeah, back.
Thank you for the talk. Yeah. The question, do you see any plans for support for adding running these quantized models similar to llama.cv via Mojo to run on CPU? So basically the GGUP or any other formats. You see that any plans to do that and like would
Yeah.
be better?
Yeah, actually, turns out CPUs are still a thing, and CPUs are actually quite fast and have a lot of really cool stuff. Max does support 4-bit quantized models on CPUs and has some of the basic features. I think we need to do more and invest in it, but it does have the basic support for that. And I mean, please check it out. Yeah, all that stuff's open source. And
Hey, thanks, Chris. So quick question. I hear a lot of GPUs and CPUs. What about stuff like the tensor and accelerators? I've been seeing they've been posting some MLI integrations as well. So what about those? Is it a plan for 1.0? And how much of it like part of being more system-wide availability, the phase 2 stuff, how much of it will leak into phase 1 for these kind of things?
I couldn't quite hear the question, but what I
Yes, so I think the question was, is how much support do we have for more advanced tensor accelerators on the GPUs?
got it.
Is that correct?
Okay, yeah. So you can't get performance out of a GPU without using all of the features. And so the Blackwell blogs that are coming out soon, for example, go into how to use the asynchronous memory copies and the TMAs and all of the features that you need to be able to get maximal flops out of it. And so Mojo fully supports that. That's a really important aspect about what we're doing that's very different. And there's a lot of systems out there that have tried to make GPU programming easy or take an existing programming language and bring it onto a GPU, but they lose the power, right? And so we're not interested in giving you something that is, it looks nice, but you only get half the flops. Like we're about unlocking the full power of the hardware. And particularly, you see everybody's spending way too much money on AI and GPUs and things like this. We want to actually push the world forward, not just try to make it easy. We also have, the whole system was designed to go into even weirder accelerators over time. We've just prioritized, and we're trying to bring it to NVIDIA and AMD and Apple, and we're just prioritizing. So.
One more question.
Yep.
Thanks. I know the focus now has been AI inference, but within the roadmap, where does training fall, or at least fine tuning of existing models?
Great question. So Modular is focusing its engineering time on inference, right? Just because our big problem is that there's a huge world out here, and focus is the only thing that keeps us, like if we try to do everything all at once, we'll never succeed at anything, right? Good news, we're not the only ones doing cool stuff. And so if you check out Nabla, for example, it's a great community project that's doing training with Max. And so you can do this today. A lot of the foundational technologies we're building, matrix multiplications and AI kernels and fusion and this kind of stuff is all completely generic. And so there's people doing that. I've heard people talking about quantum stuff and Bayesian models and like all kinds of other applications that are outside of what Modular is focusing on. But the whole point is that we should not have to do everything to enable compute. We want to do this together with everybody. Yeah. Awesome. So thank you all. I hope this is a good roadmap.
Yeah, thank you so much, Chris. And yeah, super exciting. And please go to the Modular docs, read more about the roadmap, read more about the vision. Yeah, and try out the nightlies. Okay, so let's go on to our next talk. Oops. All right, so I'm excited to welcome Feifan Fan from Inworld. Inworld is, if you haven't heard of them, you probably should, because I think that they are one of the most exciting generative AI companies that are out there. They have an incredible text-to-speech model, which boasts incredible low latency, but the voices are also realistic and highly configurable, and they really work to create immersive experiences for their users. And Inworld has also been partnering with Modular. They are one of the first partners that we've had, and it's been an incredible relationship to see their original models and the things that they've been bringing up. So please give a very warm welcome to Feifan from Inworld, and he's going to talk about how Inworld and Modular made state-of-the-art voice AI production ready.
Thank you, Chris. Hi, everyone. I'm Feifan from Inworld. So today, I'm very excited to talk about how Inworld and Modular collaborate together to solve some challenging issue in the text-to-speech domain, and we make this model ready for everyone. Especially we will explore how we solve some very challenging problems through this talk. I want to first showcase how Inworld and Inworld TTS model and Modular Max together build a demo to talk about this stuff. So a quick brief introduction about the collaboration. So we started to collaborate Modular to improve the text-to-speech model from Inworld starting from early this year. Back to that time, we have some challenging issues that we are continually increasing our model size, but the text-to-speech latency is very critical to our consumer, especially for real-time application. So we want to try to solve the latency issue and speed up the text-to-speech model as we continue to increase the model's parameter size. So we started to partner with Modular to solve this issue, and let's see this demo quickly to showcase the final result for Inworld TTS and Modular Max inference engine.
Hey everyone, woohoo! We're so excited to introduce you to the new Inworld Voices v3, which is powered by our cutting-edge speech LLM model. This model is a game changer, bringing voices that sound incredibly natural and human-like. Its realistic speech capabilities make it perfect for any application needing lifelike voice interactions.
Wow, Timothy, that sounds pretty amazing. So what makes it, stand out in terms of sounding natural?
Well, Jamie, it's all about capturing the nuances of human speech. You can really hear the authenticity and warmth, can't you?
Yeah, totally. It's like you can almost feel the emotion. So how does it handle different emotions?
Great question, Hades. The model has a wide emotional range. It can express empathy beautifully, like having a conversation with a friend who really gets you.
And what about accuracy, especially when it comes to complex stuff like numbers and dates?
Oh, absolutely, Jamie. The model excels in accuracy. For example, if you provide a phone number like 558-123-4567, it can recognize and format it correctly. Or if you're looking for a specific date, such as when the Declaration of Independence was signed, it'll accurately tell you it was July 4th, 1776. Plus, it can handle tricky text like tongue twisters with precision, such as, how much wood would a woodchuck chuck if a woodchuck could chuck wood? He would chuck as much wood as a woodchuck would if a woodchuck could chuck wood.
It's fascinating how you can switch emotions. Julia, can you show us how it works?
I can't believe what just happened. The news was completely unexpected and it changed everything.
I can't believe what just happened. The news was completely unexpected and it changed everything.
I can't believe what just happened. The news was completely unexpected and it changed everything.
That's amazing, Julia. It's like you're really feeling those emotions. What about speaking styles, like whispering?
I can't believe what just happened. The news was completely unexpected and it changed everything.
And what about nonverbal vocalizations? I heard you can, mimic things like laugh or cry.
Okay, so you're telling me the test failed because of one missing comma? I don't even know why this is hitting so hard. I feel like I'm going to lose it.
All right, focus. We can still fix this.
Sorry, I've been dealing with this dry air all day. Gosh, I really need sleep. This bug isn't the only thing crashing.
We've partnered with Modular to supercharge Inworld TTS, combining our state-of-the-art voice quality with Modular's world-class serving stack to deliver breakthrough speed and affordability for every developer. At the heart of the Inworld TTS serving stack are two foundational technologies that are part of the Modular platform. Max is a universal high-performance AI serving framework built to deliver state-of-the-art performance across GPU and CPU platforms. It combines advanced batching, graph-level optimizations, memory planning, and fine-grained kernel scheduling in a single containerized runtime with an open AI-compatible serving endpoint. Mojo is a systems programming language focused on AI kernels. It bridges the gap between Python's ease of use and speed-of-light performance, offering fine-grained control over memory layout, parallelism, and vectorized execution. Mojo serves as the foundational layer for writing kernels and graph transformations within Max, making the entire stack programmable and portable without sacrificing efficiency. Now we are conducting a live inference speed comparison between Modular and VLLM to benchmark their performance for accelerating in-world TTS model. The tool sends identical streaming speech synthesis requests to servers running each engine, using the same text and speaker to compare their respective latency metrics. Based on the comparison results, Modular demonstrated superior performance over VLLM across all key latency metrics. Modular had a lower first chunk latency, meaning users hear the beginning of the synthesized speech more quickly after the text is submitted. Modular also showed a lower end-to-end latency and real-time factor. This reflects greater overall efficiency, especially for longer sentences, and allows the system to handle a higher throughput of requests. Hello, this is a streaming speed test of in-world TTS with Modular and VLLM. Hello, this is a streaming speed test of in-world TTS with Modular and VLLM. Now let's try a much longer text to test the inference latency. Even with the substantially longer text, Modular continued to outperform VLLM, demonstrating its superior efficiency and scalability for sustained workloads. All the voices in this demo were generated by in-world TTS model. Thank you for watching. Hey everyone! Hey everyone!
Yeah, thank you. So, yeah, so I want to let's continue the talk. So the voice AI revolution is transforming around us. So it's affecting countless industries, from gaming and interactive entertainment to consumer service and call center. We see it in education and e-learning, and we see it in our cars, in our smart home devices. So the demand for natural, responsive voice interaction has never been higher. But bringing this technology to millions of users is incredibly challenging. There are 5 major hurdles we need to overcome. First thing is about latency. So the awkward pause that can kill immersion and user trust. Second thing is about scalability. So it's hard to handle millions of current users without the quality performance degradation. Third thing is about cost. So historically, create high quality real-time voice generation is very expensive, especially for the consumer application. If they have a lot of users, it's hard to scale in production. Fourth thing is about quality. Previously, the original traditional text speech model are usually very robotic. And if we want to move beyond robotic and create emotional resonant speech, it's a huge technical challenge. Last thing is about integration complexity. And managing and optimizing the entire AI stack requires massive engineering effort. So we solve this problem through the powerful collaboration between Inworld and Modular. So the partnership was simple. So Inworld focused on building the state-of-the-art impressive TTM model to create lifelike voices, and the Modular provided Max Engine, a high-performance scalable inference stack, and designed to run AI at maximum efficiency. So both teams use their own expertise to deliver this solution, and we run Inworld TTM model on top of Modular Max Engine in less than 8 weeks. So if we check this latency graph, the top line is VM's inference, and the bottom line is the Modular inference engine. We can clearly see the latency got significantly improved, especially when the QPS become higher. VM latency become significantly higher as well, but the Modular latency is very stable. Let's talk about a little bit about the text-to-speech model architecture for Inworld TTS. So majorly it contains 2 components. One is speech LLM. This is a backbone LLM. This is using an LLM model as a backbone. The second part is audio decoder. So speech LLM component will take the text input and convert it into streaming audio tokens. And the audio decoder will decode the audio token into the final audio wave files. This two-level stage architecture is very robotic and can cover very diverse voice and challenging edge cases found in the real consumer application. Having a good model is not enough. It has to be very fast. This is why we started the collaboration with Modular. Our serving stack is targeted to streaming ready out of the box. This is very essential for the real-time use cases. So, this use case, our TTS use case is actually more challenging than the traditional typical LM model, because TTS model contains two parts. One is the backbone LM model, another is audio decoder. The challenge is that we need a seamless streaming generation across two components through speech LM and audio decoder. Through this figure, we can see Modular Max engine will take over all the inference engine part and run on top of NVIDIA Blackwolf hardware. Let's dive a little deeper about that. So the entire framework is Max framework. So this is a universal high-performance AI serving framework built to deliver state-of-the-art performance across GPU and CPU platform. It has some advanced technology like the advanced batching, graph level optimization, memory planning. And in the bottom layer is the module language, as Chris introduced earlier. This is a programming language focused on AI kernels, and it gives the user fine-grained control over memory layout, parallelism, and advanced execution. So our collaboration aims to power the next generation of AI application. The first thing we want to deliver is unmatched quality. So Inworld TTS target to deliver rich, emotional, nuanced speech virtually is distinguishable from human speech. From the bottom chart, we can see the comparison with other competitors in the market. We achieve lower word error rate, and this means the TTS model can generate more accurate results compared with other providers. And we also see higher similarity score in voice cloning. So this is directly compare some leading competitor in the market. And from the right chart, this is from the Hugging Face TTS Arena dashboard. So the developer community also ranked Inworld TTS as #1 in the TTS Arena leaderboard. So this all this information demonstrate we deliver the unmatched quality for potential consumer application. Another thing is we are also blazing fast for real-time interaction. Thanks for the optimization by modular framework, and Inworld TTS can deliver the first 2 second audio trunk in as low as 200 milliseconds. And this is very essential for real-time consumer AI application, from social apps to game, from learning to wellness. From the bottom chart, we can see, compare with other TTS model in the market, if we compare from two metric, one is the first 2 second audio trunk, and the second metric is end-to-end generation latency. We can see from the model, after the modular optimization, we can clearly see Inworld is much significantly faster than other provider in the market. This solution is also radically affordable for every developer. We believe that state-of-the-art voice AI shouldn't be a luxury. So with the optimization from Inworld and the modular, we are fortunately to make Inworld TTS 1 release at a disruptive price of $5 per 1 million characters. And if we check the chart lower, compare with other leading competitor in the market, their price is significantly more expensive, and this can be a bottleneck for many consumer applications to scale. When we discuss with our potential consumer, especially initially we discussed some gaming consumer, they told us that they can't use the existing TTS solution in the market. Either is too low quality, it's not realistic from the user perspective. The second bottleneck is it's too expensive. If they want to enable that feature for all their users, they cannot afford that. So after this solution, collaborative between Inworld and Modular, we can now every developer and team from inside hacker to enterprise can integrate production-grade voice AI into their product without breaking the budget. So the collaboration between Inworld and Modular is a glimpse into the future of accessible AI infrastructure. We make it possible for every AI developer to focus on delivering the best experience to their user, to their product, and do not worry about how to use the latest voice AI agent into how to integrate and deliver the latest voice AI into their product. And with this kind of solution, the voice developer can focus on deliver the truly instant interaction, and also scale the application without the fear or cost, and also ensure seamless performance even under very heavy load. Yeah, so we are here. We invite every developer and every you to start to build the future of voice AI together with us. And we are also very excited to invite you to try the Inworld TTS playground or directly check the API doc for getting started for the integration. If you want to learn more about Max Modular, there's a website here. If you want to learn more about the collaboration and how we build the cool stuff together with Modular, to please see the joint blog post with there. Yeah, that's it. Thank you.
Yes, thank you so much. Yeah, did you want to take any technical questions or? Yeah, okay, yeah. Sure. Any questions from the audience about Inworld and their technology?
Thanks for the talk. Just a question. Based on your knowledge of what you're doing so far on TTS, do you see any of these models in the future moving into IoT devices such as watches or any other kind of end devices?
Yeah, thank you for asking. So we are also working on device model as well. So as we mentioned earlier, we have different model size for TTI model. Probably we start from 0.1 billion parameter, and then we do 1 billion parameter model, and then we go to 8 billion. And in the future, we are also getting larger and larger. That's why we want to collaborate with Modular to significantly improve the inference speed latency. As we know, the model size parameter become larger, the model performance is likely become better as well. But we want to, on device model, we want to use a smaller model and still have a faster inference speed. That's our target. So this is also what we are working on recently.
I thought the voices were interesting and quite unusual. But the question I was going to ask, Hollywood got all whacked out of shape because people didn't take some of the famous people's names. For example, say you pick your favorite actor, so we'll pick Jack Nicholson, and then you start using Jack Nicholson to do things. So there's a whole series of lawsuits going down in Hollywood right now about their ownership or their image and their intellectual property or their voice. So you particularly get anybody who does voiceovers or any kind of sort of stuff, it's really you run into this legal sinkhole. So, you're liable because you basically stole their intellectual property.
Yeah, I think the safety is very important for voice cloning, especially currently the voice model, the TTS model, it become powerful and powerful. It's very easy to clone some celebrity voice. This is the responsibility from both the platform and also from the developer. So from the platform perspective, we will have the policy that you can only use the voice you have the right to clone. And if we detected some fake uses, we will immediately disable that account or disable the misuse of the voices. And from the developer perspective, for many developers, they started to give an API in their application to allow the user allow the end user to directly clone some voices. So that will require developer also take their responsibility to make sure the safety of the voice AI usage. Thank you.
Oh yeah, thank you so much. Okay, so we're actually kind of on schedule for the next talk, but I want to give Feifan another round of applause for a great talk. And I loved the demo. That's not the first time I've seen the demo, but it's always, I don't know, I think it's always just really exciting to kind of see it in I don't know, the reality and expressiveness of the voices and the speed of it is just always really kind of cool. Okay, so I'll be giving the last talk of the evening. And this one's going to be a little bit different. So I kind of want to start out and kind of ask folks, how many of the people here have experience programming GPUs? So a few hands coming up. And like, how many of you are excited about learning how to program GPUs? Like, it's something that you're, so also a few hands. So the title of the talk is why matrix multiplication remains one of the most important problems. But what I'm hoping to do is to kind of frame this as something to show you why GPU programming is important, and in the context of a very old and kind of simple algorithm, right? And if you haven't been a GPU programmer, then it would be great for you to go and try out Mojo and try out these examples and learn how to do this and learn how powerful this is for yourself firsthand. And if you are a GPU programmer, then what I hope you take away from tonight is how easy it is to go and implement these algorithms and how powerful Mojo is to help enable you in getting more out of your processors. Okay, so for the agenda for the talk, we're actually going to talk about matrix multiplication and what it is and what the algorithm is. And then we're going to kind of put this into context because it's nice to see applications and it's nice to see why it's important in a real world context. And putting this into the context of large language models and how important it is for large language models kind of like gives you a sense of the scope and why people are still worried about an algorithm that is, decades old. And then we're going to kind of run through some implementations. And so we're going to go through a couple of naive implementations, the triple for loop things that you might have written in the past or seen in the past. And then we're going to go into we're going to start doing some optimizations, and we're going to look at how do we optimize the algorithm? How do we make things better? So we're going to talk about memory coalescing, what that means and how it works, shared memory tiling, and what sort of performance we get out of that. We had a question earlier tonight about tensor cores and how you can utilize tensor cores to really start getting a lot of acceleration and speed out of these devices. And then we're going to give a little bit of bonus. For those of you who know large language models and kind of understand the computational issues of how they work, especially around the attention mechanism, we'll talk a little bit about how flash attention and how flash attention ties into all of this. And along the way, we're going to show some performance benchmarks. And so we're going to, if you see my mouse right here, we're going to be kind of like focusing most of the talk in this region down here. Now, these are performance metrics that I ran earlier today on an A100, so an NVIDIA A100 machine, using our algorithms. And you can kind of see that there's, some dips here. Performance depends upon tuning, depends upon the parameters you choose. And so, depending upon the processor you choose, you may see a straight line going up. But you can kind of see that we start from basic CPU naive performance all the way down here, which is basically 0, and all the way up, to kind of like super fast performance using tensor cores. Okay, so who am I? Well, I'm Chris Hoge, and developer relations manager here at Modular. I have a background in applied mathematics, and so for a long time, I did math, and I did computational math for a whole bunch of different organizations. And then my career shifted a little bit, and I became involved in open source infrastructure and computation projects, and I've been working in open source for over a decade. And if you want to get in touch with me, my email's right there. It's hodge@modular.com. Please feel free to reach out. Okay, let's get started. Matrix multiplication. So formally defined, if you're given two dense matrices, A and B, and for a lot of this talk, we're going to kind of assume that they're square, but they don't need to be. Assuming they're square just kind of like makes it easier to visualize things. But they're M by K and they're K by N, respectively. And we want to compute multiplication that's defined as where each element in this matrix C is the sum of every row in the A matrix multiplied by every column in the B matrix, right? Okay, bit complicated. So visually, if you know what a dot product is between two vectors, you just multiply each element in the vector together and then add them up or accumulate them. So we take every row, we multiply it and add it with every element, and then we put that into our matrix C. And we do that for every element in here and we fill it up. Written as pseudocode, right? And so this is kind of Python code. We iterate over every row, we iterate over every column. We set our accumulator equal to 0. And then we loop over that inner matrix shape K and accumulate all of the products there. But what does it really mean? Right? And conceptually, matrix multiplication projects a K-sized set of m-dimensional vectors onto an n-dimensional vectors onto an m-dimensional space. There's a typo there that I'm gonna have to go back and fix. But essentially, you're taking a whole bunch of information that is in one system of units, and you're transforming it into another. You're stretching it and transforming it and turning it, and changing how that looks. Okay, so why is this important? Well, every LLM, whether it's Meta's Llama, Alibaba's Qwen, DeepSeek, Claude, OpenAI's ChatGPT, or even Google's Gemini's, utilize matrix multiplications at their core, right? And if you've looked at, you can kind of like see matrix multiplication in the attention mechanism, and you see like in the transformers, you have linear blocks. All of these things have matmults in them. They might be disguised as like, MLP or linear modules, right? So that's matrix multiplication. It's there in the attention matrix, in the attention, latent attention, and mixture of experts, and so on. And indeed, when you look at Llama 8B's runtime, over 83% of the time when you run that model is occupied executing some variant of matrix multiplication. And it kind of makes sense, right? If you think about how a large language model works, you start with words and you turn those words into values. And so those are tokens. And then you turn those tokens, which are, so you can imagine that your input text is just a long vector of values. And then you turn that into an embedding, right? You add dimensional context onto that. And all of a sudden that vector has turned into a giant matrix where every row can be considered a context of the sentence that you gave to it. And then the large language model is performing a series of transformations against that to try to match context from different parts of the sentence to another, and then predicting what the next word will be, right? And decoding all of that. And when you start looking at this, all of it is transformations and a ton of it is wrapped up in linear transformations. Not everything. We need the nonlinear transformations to kind of get the magic going, but the linear transformations are a huge part of this. Okay, well, so let's get started. Now, for these examples, we're going to be using Mojo and we're going to be using Max. And the way that we're going to kind of do this is we're going to work through Python sitting at the top of this through the Max graph interface. So we'll just go through this really quickly, but essentially what we do is we think of the Max graph interface as a high-performance computation framework that lets you build and execute efficient machine learning models. And it gives you a flexible way to define a computational workflow as graphs using a Python API. And so it's how we take the magic of Mojo and kind of lift it up to Python so that we can like essentially meet users where they're at, right? So that we can implement a whole bunch of super fast operators in Mojo, and then we can kind of expose those in Python for you to work with. And so if we look at the code, this is just kind of, a little bit of scaffolding here. We define a matrix multiplication operation, which will take in two tensors, and then we tell Max Graph where we can find our custom kernels. And then we define a graph where we take in two tensor types as our inputs. We point it to where our custom Mojo kernels are. And then we define an output as a custom op. And you don't have to understand what all this code is, right? I just want to show it to you so that you understand where we're coming from. And as we define these operations, the max graph library is going to be able to dynamically compile them. So you don't have to go out and write any sort of your own scaffolding, your own make files, anything like that that you might have to do in C++. The max Python interfaces will handle this for you. Go out, compile the Mojo code, it will load it in, and it'll run these operations. All right, so I just wanted to give you a flavor of like kind of what that looked like from the Python side of things. But let's get to the real meat of this. Let's start implementing some kernels. And we're going to start with the naive matrix multiplication in Mojo on CPU. We're going to go back and we're going to implement that, that pseudocode, those 3 loops, and we're going to do it on a CPU so we can kind of get a baseline. All right, so how do we start out? We create a Mojo function, and it looks a lot like a Python function. We define our output as a managed tensor slice, and this is just, a type inside of Mojo that allows that, that kind of, manages your memory for you and kind of allows you to create and use tensors in an efficient way. And we define our 2 inputs. We specify the data type that we want. And so this is like a nice feature of Mojo. That Mojo has these sort of generics where you can write the algorithm a single time, and then you can, and then at compile time. So anything inside of these square brackets here is telling Mojo that this is a compile time parameter, similar to templates in C++. And that this algorithm will be compiled for the output type that you want and for the rank that you want. So we take these, we take the shapes of these matrices and we find our M, N, and K values, right? M is the, K is the inner dimension of these. And then we just loop over every row, every column for every item in the vector. And we do our accumulation operation, right? And that's it. This is what the algorithm looks like in Mojo. Pardon me? I still can't hear. So this is, Brad, you'll have to help me here. This is the output rank of the tensor. Yeah. Right. Right. So that so when we we're talking about for all of these examples, we're talking about 2-dimensional matrices, but for a lot of applications, you actually have higher dimensional tensors. And so you can imagine sending in a batch inference job, right? Where you can have, where the rank of the tensor is going to grow, where, each batch can, each rank is another batch that you're sending in through the inference. And so, in some ways we're just specifying to the compiler, like how many dimensions these matrices are going to have, right? Or, because they're being represented as tensors. Okay, so with naive algorithm on a 2.5 gigahertz AMD server grade processor, right, which is hosting our A100s, we get about 1.6 gigaflops, right? Not amazing, but it's a nice baseline to start with, right? It's nice to understand the performance that we get out of this. Okay, so what are the problems with running on a CPU, right? Why can this be problematic? Well, this algorithm's serial, right? We haven't considered any parallelism on the CPU at all, right? Now, Mojo does support SIMD as an intrinsic type. We didn't take advantage of that. But we didn't take any advantage of parallelization on the CPUs or through GPU cores. And it's order n cubed, right? And so as your matrices get bigger, this gets a lot more expensive to compute, right? And so you want to look for ways to speed this up. And we can do a lot better. So let's start working through some other optimizations. right? Well, actually, at first let's talk about we talked about some of the limitations of CPUs. They're limited to the number of cores they have. And lower end CPUs, server CPUs have about 32 cores. High-end CPUs have about 128 cores. And while SIMD can give us some additional parallelism, it's still limited. How can GPUs help on this? Well, they offer massive parallelism. A modern GPU, like a B200, can handle over 100,000 threads simultaneously, right? So that's a massive improvement over CPU cores. And it makes it an ideal choice for the sort of repetitive data parallel operations that you see in matrix multiplication. Like you have all of these dot products that are happening independently of one another, right? It's kind of like the perfect thing for parallelism. And when you think about programming GPUs, like it's a different mindset than when you're programming CPUs. So this is probably familiar for a bunch of you. Like you have a whole range of data, you want to do computations on it, and you set up a for loop in that, right? Everybody's used a Python for loop or a loop in C++, and you process the data and you feed it into some result. The way you want to think about it on GPUs is that this is an opportunity to map thousands of parallel threads directly onto the data. And so you're taking away the loop. The GPU scheduler handles the loop. And you become concerned with how do you move memory into the GPU so that the scheduler can hand that work out and the work can be done in parallel and do it effectively. Okay, so now it's time to move on to the naive matrix multiplication in GPUs. And so we're going to implement the exact same algorithm, but we're going to think about it in terms of parallelism, think about it in terms of getting it onto as many cores as possible. But let's start by looking at simplified GPU architecture. This is a super simplified diagram, right? A GPU has a whole bunch of streaming multiprocessors. And each of these multiprocessors has just a whole bunch of cores that they'll be able to execute. Now, there's this concept of blocks, which is a unit of work that you're going to send out to a GPU. And so you organize your work according to blocks, and then the GPU will schedule that work onto a streaming multiprocessor. And then you program these kernel grids that kind of like schedule this work out, and they're going to be executed. We also have global memory, which is usually a pretty large pool of memory that is accessible by all of the streaming multiprocessors and all the cores, but it can be a little bit slow to access. And then you have a local shared memory, which is much faster, right? Keep these concepts in mind as we kind of work through this, because it's going to become key when we talk about some of the optimizations we have. Okay, so let's look at this implementation. We have our naive matrix multiplication. We specify at compile time, remember that these are in brackets, a data type, and a layout. And these block sizes will become important later. Right now, we can ignore them for now. And we have our inputs and outputs, so our three different tensors, or three different matrices that we put in. Now, one thing that you want to consider when you're programming GPUs is that every computation has identifiers that are associated with it that help you in that thread understand where you are in the context of everything else on the GPU. And so when we talk about these blocks before, they are often laid out in terms of X and Y coordinates, because that makes it easy to map onto the data that you're working with. And so we grab a block ID, which has a dimension. And so how big are these blocks in the X dimension? We multiply that by the ID of the block that we're on. And so that puts us into an X location on the grid, along with a thread ID, right? And so this specifies a row that we're going to do the computation on. And similarly, we do this for the Y dimension of our block. Then we make sure that we are actually inside of the bounds of our matrix, because we don't want to read out the bounds of our memory. And then we loop over every index K, and we do that one dot product on a single core. And that happens right here in this accumulation step. And then when that's done, we set the value at the row in the column that we computed to the value that we computed. Now, you'll notice that we're missing kind of the outer loops on this, right? We got rid of those 2 outer loops, and that work is being handled by the scheduler for the GPU. Same algorithm, and you have to think of this as running thousands of times for a large matrix. And what we see when we run this is that we actually get incredible performance out of it, right? I mean, already almost 1,000 times better. Like, just by using the exact same naive algorithm and going from a single core to thousands of cores. But we can actually do better, right? Because we're actually not utilizing the memory available to us as well as we can. And so our next optimization is improving memory access with memory coalescing. Okay, and to understand coalescing, we need to understand warps. A warp is a concept kind of on NVIDIA GPUs, but it's common to like other GPUs too under different names, where they're groupings of 32 threads in a block. Right, and so a block is divided among, has multiple warps that are 32 threads each. And the characteristics of these are, first of all, is that with an asterisk, threads in a warp will always execute the same code. Right, and so you can get them to work in lockstep with one another. The second is that sequential memory access by threads on the same work can be grouped and executed as one. And so remember back in our last algorithm, we had to go out and we had to grab all of the memory, we had to grab all those values from our global memory and bring those onto the thread. What we're going to see is that we didn't do that in a very efficient way. And that we can improve the speed of our algorithm by improving that memory access. And you can think about it like this. When a warp is reaching out, and so you can think of this as a warp, and I know this is only 8 units wide, normally it would be 32, but we wanted to fit a couple warps on the screen here. When it's reaching out to memory, this is the global memory, it is able to if all of the memory in these operations is together consecutively, it's able to pull 4 of these in at once, right? So it can pull them in and it can turn 4 memory load operations into 1 memory load operation, just because of the way that we've laid out the memory and the way that we're accessing the memory. In our previous implementation, this wasn't our memory access pattern at all. We were reaching all over memory to grab different parts of it. And so it meant that we were accessing memory in kind of like one of the most inefficient ways possible. So with this in mind, keeping in mind that we want to have consecutive memory access when we're doing this coalescing operation. Oh, and this is actually kind of like, this is a nice illustration of what the memory access looks like. And so in this naive kernel, you can think of every one of these bars as threads that are running on a single warp, right? And so this is running on a warp, this is running on a warp, and this is running on a warp. Memory is laid out row major, and you'll notice that on every warp, none of these memory accesses are consecutive, right? There are large strides between these, and so we can't take advantage of coalescing. And similarly, on this column here, we're jumping through memory, and so there's no memory coalescing here. And so with each of these computations running on different threads in the same warp, there's no benefit, right? You're not getting any memory benefits from that. But if you reverse that, because the nice thing about linear computations is that you can do the computation in any order that you want. If you switch this so that on one warp, you're always reading across the same column, you're preserving memory access across that row. And then here, when you're doing the dot product on the B matrix, if you're loading the memory into the warp sequentially across here, then you can start taking advantage of memory coalescing. Then you get tremendous advantage. So what does this look like in code? Can anyone spot the difference? Right? I know that it's like, if you look at it, it's the same algorithm, basically. The big difference here is that we swap our block IDs, right? For the rows, we're instead accessing against the Y dimension of the block. And for the columns, we want to access sequentially across the X dimension of the block. And so the Y dimension is going to change more slowly. This X dimension is going to be sequential across each warp. And so, to kind of like make it, to make it a little more, these are the only differences here, right? We're accessing the blocks here across the X dimension, blocks here across the Y dimension. We just flip that around. And when we implement that algorithm, we get a significant performance boost, right? We go from 1444 gigaflops to 2663, right? And so from that one change of how we access memory, you've accelerated your computation even more. All right. This is actually why it's nice to be able to like work through these examples and kind of follow through this, because it gives you an intuition of how GPUs work and how you can write optimal algorithms and how you need to kind of start shifting your thinking from traditional CPU-based programming to GPU programming. But we can do even better. And I actually think that as you're kind of learning about like matrix multiplication and GPU programming, shared memory tiling is kind of one of the most important concepts that you can pick up. Okay, so up to this point, all of our kernels have loaded data directly from the global memory, right? And we talked about that a little bit before, that access to global memory it's easy, but it can be a little bit slow. And each streaming multiprocessor has shared local memory, which provides much faster access to blocks, right? So if you can preload memory into there and you can utilize that, it's a smaller memory bank, and so you don't have the flexibility to just grab anything you want. But if you can do your computations from there, you can accelerate your computation, right? So going back to our simplified GPU architecture, we want to start moving data. We want to move data from the global memory to the local memory, and then we want to do the computation from the local memory. And so the idea here is you copy chunks of tiled memory, computing portions of the matrix multiplication, right? Previously, we were doing an entire computation on one thread. And instead, we're going to take tiles, we're going to take these chunks, we're going to do portions of the computation, and then we're going to iterate over these blocks, and we're going to accumulate the final result into C after we've done that blocked computation. And hopefully you're keeping up, hopefully you're kind of like getting the high level ideas of this. I'm really hoping that I'm priming you for all of this. We have documents that cover all of this, examples, tutorials these are drawn directly from, and so you can go home and try this yourself. Okay, so this is where these block size indexes were coming in from before, right? We saw those before on an implementation, and this is where they're coming into use, right? We're going to specify the size of the blocks across each M, N, and K dimension that we're going to be tiling against. We then compute a block index that we're in, right? And so our rows and our columns are going to be based off of kind of where we are in the block. And so we do this by taking the floor division of that and also the remainder division of that. We're also going to allocate a tile. And so this is some special magic that we have in Max, where we're going to have our destination data, right? So this is the size of the tile that we're going to be writing data into. And then here's where we allocate our shared memory. And so we have this thread builder, which takes a type here. We specify the type of matrix that we want to build, and so it's going to be row major. And then we allocate the memory, right? And we do this for both the A matrix and the B matrix. And so this is the shared memory. We're going to pull data from the global memory, and we're going to put it into there and run the computation on it. Then we initialize our accumulator. So here is where we load our layout. And so layout is an affordance that we have within the within the Max libraries that allow us to define views into other data. And so you can think of that there's a large data pool, you have a large matrix, and with matrix programming and GPU programming, it's very helpful to look into that data with different views. If you try to do that manually, it becomes computationally expensive. It's very error prone, right? Because you have to compute offsets, you have a lot of this kind of math that you have to take care of to remember, like, how big is it? How big are my strides? How long, where everything's going? And this gives you a nice way for Mojo to be able to say that, like, oh, you have this layout, it's defined in this way, it's this view into this other data. We can move that into other data, we can perform computations on that, and it takes the burden off of you of having to manage that view. Okay, so we get the tiles of A and B for the computation, and so we pull this from the memory. We pull this from the global memory into the SRAM, right? And so this is this is similar to copying data. The NVIDIA CUDA has an operation that does this. This is very similar to that. Now, because we want to make sure that every thread has access to this data, we need to make sure that we do an asynchronous copy and wait all on that, and then synchronize all the threads so that they can run at the same time. So we want to make sure that all of the memory across all of the threads that we're running is consistent, right? So this is another aspect of kind of like this parallel programming, is like when we're having the shared memory, everybody needs to have the same view, right? And so we want to synchronize that. And then we run our loop. And so for the size in our block, we do an accumulation. We synchronize, so we make sure the accumulation across all the threads is complete. We do that across a whole bunch of blocks, and then we return the accumulation. And once again, we see a huge jump in performance based off of this. Like by going from global memory access to batching the memory motion into the shared memory and working on that from the much faster memory, we almost have a factor of what is this, 1.5, 1.8? Yes. Pardon me? So global memory is the on-device GPU memory. And then the shared memory is the local memory to the streaming multiprocessor. Yeah. Oh, yeah. Yeah, I don't. Yeah. Yeah. We'll yeah, so we'll it's heavily device dependent too, right? Okay, so one thing that I wanted to talk about, and there was a question earlier about, so is about tensor cores, right? GPUs just don't kind of have these individual cores. They also come with tensor cores that are optimized for matrix multiplication. And it's beyond the scope of this talk to dive into it much deeper, but it's important to note that all of these examples are using traditional GPU programming techniques. And so, right, so we're using the cores on and not the tensor cores. But I do want to say, and these modern GPUs have the tensor cores that are optimized to perform this matrix multiply accumulate operation. And Max actually contains interfaces that makes it more ergonomic to program these dedicated hardware units. Right. And when we use these hardware units, and so we're not going to go into the detail of the code here, we actually see that we just have a massive improvement, right? It's just utilizing the tensor cores and taking these tiled approach to the tensor cores gives some really great performance. Okay, and so while Max and other accelerator libraries will provide you with pre-optimized matrix multiplication operators, understanding the optimizations behind matmul, I think, are actually useful for developing other GPU optimizations. Right, and this is where we kind of like get into this idea of flash attention. So if you look at the attention mechanism in large language models, they consist of several matrix multiplications. And so typically on these diagrams, you read from the bottom up. The data flows from the bottom up. Your Q and your K go through a matmul, your Q and your K computations. There's a scale, a mask, and then there's a softmax in here, right? And the softmax is a nonlinear optimization that takes kind of like, it's almost like an exponential average to kind of like create more of a probabilistic view into what are the most relevant items in that, but it's nonlinear, right? So a lot of what we talked about the linearity and the being able to shift those operations around doesn't hold anymore. And then there's another matrix multiplication here, and this set of operations and the size of the attention mechanisms and the number of the attention mechanisms could possibly turn this into a massive bottleneck for large language models. But to address this, right, so there's this idea if you had to materialize that entire thing, it would just slow everything down. But instead of materializing the entire attention matrix in memory at once, flash attention actually takes this same tiling approach, this same kind of tiling algorithm, where it processes small chunks of queries, keys, and values sequentially, and it computes attention scores by applying the softmax in an online manner within each tile, right? So if we think about the same algorithm that we had before, where we were kind of like looking at the tiling and applying these chunks and like doing these accumulations and saving those operations while we're bringing in memory locally, the key innovation is the online softmax technique maintains running statistics across the tiles. And it allows it to actually compute a numerically stable softmax without needing the entire row of attention scores, right? But when you look at the flash attention algorithm, you can kind of like see that in the context of this tiling algorithm and see how it comes out of that. And if you want to see more information about this, we actually have one of our internal engineering documents that's published about this. If you go to modular.github.io, this modular subdirectory, you can see where we've started open sourcing a bunch of our engineering documents, where we kind of talk about how we tackled some of these problems and how we approached taking research into production inside of our open source kernels. So this is kind of like bringing us to the end of the talk, but I wanted to share some additional resources with you. The first is that this talk is available on GitHub. And so it's available as code at github.com/modular/workshops. We have a few other workshops here that we've delivered that you can go and you can look at those too, and you can download those. All of these links are available there. If there's anything you wanted to look at, follow up, this is the place to start. These examples are taken from our matmul custom op tutorial. This is at docs.modular.com in the tutorial section. It covers all of these optimizations. It goes into depth and several others, right? And it's a great place to start, and it's a great thing to work through for both learning Mojo and for learning GPU programming, learning layout tensors and how those work and how those help you optimize your memory access. But I can also highly recommend Simon Boehm's matmul optimization notebook. This is kind of a classic piece that goes through all of these optimizations and really gives like some incredible detail about how every one of them works within the context of the hardware. I highly recommend you read it. It's kind of it's a well-known piece. It's legendary in in the industry, and it'll really unlock a lot for you. And finally, we would love for you to join the Modular community. At modular.com/community, we have a ton of links to our forums, to our Discord, to our GitHub. We would love to see you there, answer your questions, help you solve your problems if you want to contribute. We've got great swag for contributors. You know, and I want to say too that a lot of this talk was drawn from these resources, right? And so some of the diagrams came from Simon's blog, came from the custom ops tutorial. All the code came from the custom ops tutorial. And we're also excited too, Chris alluded to this in his talk, that tomorrow we're releasing the first part of a 4-part blog series about how we wrote matrix multiplication, optimized matrix multiplication for Blackwell. And we were able to build out a state-of-the-art algorithm in just 8 weeks. It's an incredible deep dive. It actually starts from the naive algorithm with tensor cores, and it goes from there. And it's going to be an incredible read, and we're really excited to share it with you. We're also hiring, right? If you want to be a performance engineer, or you want to work on kernels, or you want to work on models, we have a ton of roles open. These are 6 engineering roles that, you know, cover cloud inference, generative AI performance, kernel engineers. Again, if you want to follow these links, they're all in the slides for the workshop, and so you can go look at those directly. Or you can scan the QR code that'll take you to our jobs page, where you can see all of the jobs that are available. But yeah, that's, oh, yes.
We accidentally said something that was not true earlier. Brad, can you set me straight? I made a mistake. Sorry about that.
So I have to apologize. So earlier when we said that the Apple Silicon GPU support would be out tomorrow with the nightly, I was wrong. It actually launched 20 minutes ago. So, so if you go, like, so I posted in the Max GPU Discord channel the flag you need to set, what you can try out. We have one example you can test out, kick the tires on, Apple Silicon GPU support, and also posted in the forum. We have a thread on this, so go check that out as well. I'll also mention that included the stuff that Chris was talking about, like the default trade implementations. That's also with this live with this new nightly. Oh, and I think, Chris, did you mention that we also have stack traces in Mojo now? So, you know, that's a kind of a new thing.
Also, don't you have some basic consumer AMD GPU support? Oh, there's some pretty cool hardware out there. I don't know.
So apologies. I got that wrong earlier.
It's here for Brad. Yeah. Yeah, in all these examples, so we have a ton of consumer GPU support right now. If you have an NVIDIA GPU, you have a consumer AMD GPU, chances are you can get this to work on it, right? And so you can go try it out, try out the examples, get started with it. But questions? Yes.
Let's see. So this could be like a little bit beyond the scope of the talk, but if you have like a really big map mole you want to do, you want to split it across GPUs, like, is that like a thing handled by Max, or like a nickel thing, or like a, where does that sit in the space?
So yeah, you can totally do that right now with Max. So Max has multi-GPU support, and so you can actually do this stuff. Right now it's a little bit manual, and so you have to actually produce different graphs and put them on different GPUs manually. We are working on a bunch of stuff that's not quite ready to go yet for having sharded tensors and other higher level abstractions, which will make it much easier to do so. And so we're investing in building into all of these levels of the stack, and we want to make sure to get, just like we talked about building Mojo, where you get the foundation right, and then you get the next thing up, and the next thing up, and the next thing up. Same thing at the Max level. And we want to build Max into the world's most epic AI framework over time, and it takes a little bit of work to get there. And so we're building into this now. So yeah, so the answer is yes, you can totally do that. You need to work a little bit at it right now. And if you have questions about that, please ask them for them.
Yeah, thanks for walking through the Mojo GPU kernels. So I see there is a, like features like thread ID and block ID, which is exposing like GPU, architecture, like very, very low level features. Also see there is like tensor and layout. So I wonder is like comparing with like CUDA, is there all those CUDA low level features exposing through Mojo, and also those higher level like layout tensor, are they a language feature, or there are some library interface implement on top of the module language?
Yeah, I mean, that's a great question. So for the devices, you know, it's hard to get away from like the lower level, you know, architecture, right? You know, you need to know what thread you're on. You need to know what block you're a part of, right? And it's built into the architecture of the device, and it's also you know, it's just like it's how we think about, right? It's how we reason about this, and it's a very effective programming model. Now, when we look at things like the layout tensor, all of these are library additions, and so you know, we are you know, trying to build these really highly optimized interfaces to like give users great affordances. And so you know, when you look at the Mojo language, almost like most of the interesting things are actually library features, right? And so you know, so you know, so the layer tensors are, you know, are kind of these like higher level abstractions that we're looking at. And when you kind of like look at like, you know, the examples that we've done here, like the matrix multiplications, right? Chances are, unless you're bringing up new hardware, you're probably not going and writing your own matrix multiplication, right? You know, libraries. But, you know, so we also include a bunch of highly optimized operators as part of the Max framework, so that you can like, so that you get matrix multiplication, you get softmax, you get layer norms, like you kind of get all these things that you need to build, you know, to build applications. But we try to make it so that they're generalizable both across the CPU and the GPU. And you'll even see that like in a lot of the examples that we give, like we actually test to see if the CPU is there or the GPU is there, then we fall back to the CPU. And a lot of the examples work just fine, right? Without really any modification. Yeah. Yep. Right. We're trying to write these so that they are hardware agnostic, and you know, the reason being is, you know, because these devices, they share a lot of they share a lot of core like design and functionality between them. And when you start writing these kind of like hardware agnostic features, it means that when you write an algorithm that can run on like NVIDIA architecture, it's actually very easy to port it over to AMD architecture. And we've seen this internally where we're able to like look at emerging hardware that's coming out of AMD and take a lot of our existing algorithms, and without too much effort, we just kind of like we tune parameters based on the device. We can bring our algorithms from one device over to another and start getting really incredible performance in almost no time at all. Yeah.
And if I may add, on the specific question about layout tensor itself, layout tensor is defined in the library, and layout tensor is really kind of only possible with the compile time meta programming capabilities you have in Mojo, that you can at compile time go and handle these layouts for arbitrary architectures, arbitrary devices, and work with that. So you can actually see, if you go to look at our layouts module, you can see the full source code for layout tensor. There's no magic beyond just compile time meta programming written in Mojo for Mojo.
Yes.
As a follow-up to the last question, so NVIDIA cards and AMD cards, they're kind of close in architecture. How do you look towards supporting architectures which are different, maybe like Cerebrus and Grok, where you don't have HBM as much, and they're focused on SRAM?
So Brad, so it's about hardware architecture support? Uh-huh.
And like big chips like Cerebrus, which are focused on SRAM.
Okay. Yeah. Maybe you could.
Yeah, so a lot of in this talk was about doing emoji optimizations, which are basically repeating what people would do in CUDA, but in Mojo. And then you have different types of chips like Cerebrus and Grok, where you don't need to do that same kind of tiling. So my question is like, how do you see developer experience for people who want to migrate between those architectures?
Yeah. So do you want to take this, Brad, or do you want me? Yeah. So, I mean, I think that like, maybe if I understand the question right, I think like maybe like a good example of this is like Apple's Metal architecture, right? Where you have everything is on a chip and it has shared memory. And so you don't have a lot of these memory movement operations that you have to do. Right. And, it means that you can't really get away from having to understand the architecture that you're working with at some level. But the hope is that the generalizations that we provide allow you to address the different qualities of the architecture, more quickly and kind of in a more generic, in a more generic way. And so part of this is as the Mojo language grows right now, like right now we're really focused on these kind of like traditional GPU accelerators, but we want to be able to open the language up more so that, if you have a different architecture, you're actually able to provide a driver. So kind of like an engine that like allows Mojo to target that platform. And if you handle the intrinsics of targeting the platform at that level, then you should be able to leverage the kind of like generic properties of things like the layout tensors to write effective algorithms that match the memory layouts that you would expect on these other sorts of accelerators. Does that answer your question? Is that kind of, yeah. Okay. Well, thank you everyone for joining us. Feel free to enjoy more of the food and talk with one another. And we hope you had a great evening.